What is Graham's number? You may have heard of how incredibly large it is. It's so big, it's larger than the number of atoms in the known universe. But what does that matter if it's just some number that some mathematician arbitrarily made up? What's the use of Graham's number? To understand Graham's number, we need to understand Ramsey's theory. And to understand that, we need to understand complete graphs. This dot is a K1 complete graph. 2 dots connected is a K2 complete graph. 3 dots connected to make a triangle is a K3 complete graph. These 4 dots can make a K4 complete graph, but for a complete graph we have to have every single dot connected to every single other dot. Because these 2 dots and these 2 dots aren't connected, we need to connect them for it to be a K4 complete graph. And this is a K5 complete graph. Let's color each line one of 2 colors. Here we have a K3 complete graph within the K5 complete graph, all the same color. Now let's color it a different way. Now there's no K3 complete graph all in the same color. And so, when we color the lines of a K5 complete graph one of 2 colors, part of the time we'll end up with a K3 complete graph all in the same color, and part of the time we won't. What would it take so that it happens every time? Let's try a K6 complete graph. Here, we do have a K3 complete graph all in the same color, and that's going to happen every time with a K6 complete graph. This illustrates R33 equals 6. The 3 just means that we're looking for a K3 complete graph, and the 6 means that it's a K6 complete graph that will always give us a K3 complete graph. Now, we've done a more simple problem with Ramsey's theory. Let's try a more complex one next, one that deals with cubes and something called hypercubes. Okay, so here we have a cube, and it's a lot like the complete graphs in that we have every vertex connected to every other vertex. And in it we have a K3 complete graph all in the same color right here, and there are a couple of those. We have K2 complete graphs everywhere because every line is a K2 complete graph. But I don't see any K4 complete graphs all in the same color. I wonder what would happen if we were to break this in half and see if there's one in the middle. So here we have a K4 complete graph all in the same color. But would that happen every time with a cube? No, there are certain ways we could color our cubes that it doesn't happen. So what about a 4-dimensional hypercube? A hypercube is just the equivalent to a cube, but it's more than 3 dimensions. So a 4-dimensional hypercube would not always have one. What about a 5-dimensional hypercube? Not always. A 13-dimensional hypercube? We don't know whether or not that would work because it's so complicated, mathematicians haven't been able to try every possibility of coloring, so we don't know about that one. What about a 7 million dimensional hypercube? We still don't know whether or not that would be enough. What number do we know would always work? Graham's number. Graham's number is the lowest number that we know would always work, and that is the use of Graham's number.